Hello, welcome. My name is Rick Wood. I'm Managing Director with Rollon Corporation, and I'm here to talk about a really exciting topic of how to make your linear guides fail. Hopefully that's of interest to you. How many people have actually used linear guides and had them fail in their application? Any? Nobody yet. Okay. What we find out, I've been working with linear guides and linear motion technology for nearly 20 years now, and what we found is we've really been able to distill it down to there are only really 5 different ways that linear guides and linear motion will fail. The first is misalignment, excess speed, contamination, improper lubrication, and possibly a crash. Those are the 5 things that really, when we distill down to the end of the day, those are the things that are really the common denominators. So we'll try to pop through each of those and give you a little bit of an understanding of what each entails. Misalignment, there's really 2 different types. First of all is the initial setup of the linear guide. So when you're doing the assembly, trying to make sure that the guides are parallel is very important. And so if the 2 guides are not parallel, what you're going to have is the one rail fights against the other in the case you have a parallel rail system. The other reason is a poor mounting surface on the machine frame. What happens is, with a high precision linear guide, you need a very high precision, high accuracy frame and machining surface in order to mount those 2, because the linear guides typically will mimic the surface that they're being attached to. If in the case that you don't have that, there are options in ways of using technology, different kinds of technology, to mitigate the fact that you don't have a very fine and advanced mounting surface. But the deal is, you really have to look back, and you go backwards and say, okay, my accuracy requirement of my axis is this. And so you want to be able to spend the amount of money that's appropriate for the machining. So if you're making a high precision machining center, you have to machine a high accuracy machining base. But if you're just doing a very simple pick and place that does not require a high degree of repeatability or a high degree of accuracy, then maybe you don't need to machine the base as tightly. The thing when you do misaligned guides, what happens is you have unequal wear between the 2 rails. You'll introduce a load at a certain point. So if the rails are bowed in, for example, you'll see like a pinch point in the rails, and you'll see a failure. The failure points will actually mimic right or wrong in the places where the misalignment occurs. So a lot of times you might even see a loading coming from the side in a particular part of the rail. A lot of times that's an indication that maybe there was a wiggle or a place where the rails were not aligned properly. These shorten runner block life or the guide life, and they also reduce the performance. This is a place that you would see an increase in maybe your torque from your servo motor. So again, back to the cost, actually, you can mitigate the problem with a linear misalignment by improving the machining surface. The other part is you can choose an improved installation process. Sometimes you can just set one rail straight and then float the other rail in, or sometimes I've seen even people float both rails in. Another option is to choose a self-aligning guide. There are self-aligning guide products that will allow you to have a great deal of angular difference here, as also physical differences here. Sometimes you can also use like a round shaft super bushing, but again, those have rigidity issues, and you have to, again, you're always trying to balance what is what are the design characteristics. The current roll-on technology that we use, we have a little bit of rotational freedom in this side, and then we also have a sliding mechanism here, so that in the case that the two rails are not aligned properly, we can both manage a vertical misalignment as well as a horizontal misalignment. Second type of failure can sometimes be excess speed inside the guide. This is another part that, if you overspeed a typical linear guide, THK, Bosch, NSK, ENA, they all make a great product, but you have some physical limitations because of the recirculation nature of the balls. You can only go so fast, and you can only get the balls accelerating around the end and coming back into the load zone at a certain speed. A lot of times when you're dealing with an excess speed issue. It's a limitation. It's probably a front-end design limitation. If maybe you've over-spec'd on the guide. The other thing happens too is, this maybe goes to the last point, is crash. What we find is a lot of servo motors, the manufacturers, when they use default settings that come right out of the box, sometimes they have 10 meters a second or 100 meters a second programmed into the actual speed of the servo, and so right out of the box they go really fast unless the control guy knows to bring back his parameters into more of a rational linear motion ball screw kind of speed. When you do run things too fast, you end up with, I mean, like a THK or a Bosch linear guide, you'll end up with balls on the floor. That's usually a common thing. How do you know that it's failed? Well, I've got balls on the floor. That's a pretty good thing. The other one is just you'll also see a lot of premature wear and reduced life expectancy. When we are designing and understanding how a bearing is being designed in, we use this typical bearing load formula. The C over F cubed times 100. The C is the capacity of the bearing. The F is the force that we're going to apply on it. It is a cube function, and it gives us an answer in kilometers. There are sometimes service factors also that you might want to investigate to see. There are things when you're going really fast, there might be a reason to have to reduce this ratio. But again, typically, how do you manage that ratio? If it's a 10-to-1 ratio and you need 10 million meters of life, well, that's 10-to-1, 10 times your load capacity versus the actual load on the bearing, and that's load per bearing. Another type is contamination. And I think I actually have an interesting picture here for contamination. A lot of times you'll have dust, debris, garbage, things coming off the metal. Our last guy was talking about carbon fiber. I mean, carbon fiber and those kind of composites are really bad. You know, you come to a carbon working area, and the guy says, "I'm failing." The guides are failing. You say, "Yeah, I'm sure they are." I mean, it's pretty important. So, using something like a vacuum technology, positive pressure, things to try to deflect the contamination away from the bearing is a pretty important thing. You know, obviously, what happens in a linear guide when you get a piece of dust or a piece of dirt, the roller or the ball, the rolling element goes over that piece of dirt. It actually digs that piece of dirt into the raceway. Eventually it just becomes like the road surface, where eventually that debris or that particle pushes down into the surface underneath. Then the surface starts to fail. Eventually then it breaks away and a pothole becomes. Once you get a pothole, then it dents the next ball. That dent then transfers into the next one, causes another one, and that's the spalling process that you'll see a lot of times. So certainly reduces performance, and it's something that accelerates the failure. This is an application I had a while ago. In this case, it was a woodworking manufacturer, and he assured me that there wasn't all that much. There was a lot of dust being generated, but they had this really big vacuum that was pulling all the dust away. So they operated the first 3 months and forgot to turn on the vacuum. So at the end of the 3 months, we actually packed the whole actuator full of sawdust. And by the time we were done, the sawdust was compacting on either end of the module and pushing out the drive ends of the module out. And then finally, he was really mad because his actuator failed. In this case, actually, we were lucky because the seals on the ball screw are highly effective. And you also see, you probably can't see it there, but the rail actually didn't have any wear on it either. But the runner block was pretty much destroyed from the constant impacts from the sawdust pushing the ends of the bearings out. So this is the case where we actually had balls falling out, and this is a lot of grease, and just it wasn't very pretty. Things you can do is make different physical contaminant barriers, have fluid coming across. A lot of times, though, in the new area, we don't want to have a lot of grease hanging around. We don't want to have a lot of mist in the air. Everybody's looking to get as clean as possible. Another way to do it is with a more contaminant-resistant bearing. On this previous example, you see that actually the ball contacts the rail, and that's where the load is transferred. In a roll-on example, sometimes you can actually have a roller where the bearing is inside and sealed, so you're not going to impact And even if you have a piece of dust right there, it's not going to ruin your day so much because it won't be as susceptible to having a very small piece running over a small piece of dust or dirt. Another type of failure we've had and seen is the improper lubrication. There's actually two ways to get it wrong. You can do too much and you can do too little. And I had one guy, he installed his module and he ran it for about 6 months, and it started squeaking. He said, "What should I do?" I said, "Well, grease it." And usually, depending on the actuator and the brand of actuator you're using, the grease cycles are quite long, but it does require grease. And a linear bearing, when you have too much grease, typically that bearing will shed the grease in somewhere else in the environment. That can cause an environmental problem as the grease falls down and gets in the places it's not supposed to be. However, too much grease inside of the rolling chamber can also cause excess heat. We also see that sometimes with mist application systems, a lot of times they're putting a lot of, and the machine tools, the old saw was to have a Trayvon system pumping a lot of oil down through the system. Sometimes you can run close to a 55-gallon drum of oil through a ball screw in a year. We've seen that happen as well, and it doesn't do any good. It's not helping anybody. Again, without the right lubrication, you're going to see premature wear and failure, poor performance, contamination. And usually you can tell if it's not lubricated, like in a ball screw especially, if it's not lubricated, you're going to see it start the heat build up, and you're going to see temperature change, evidence of temperature change inside the ball nut. Sometimes it'll turn blue or a different color. That's evidence that the lubrication had failed. I have to say, automatic greasing systems they're expensive and can over lubricate. And I think in today's environmental conditions, we don't want to. I think that's probably a solution that's passed. Another way is to seal the lubrication inside the bearing and then leave the rail and the bearing surface. This surface sometimes can get away without lubrication, but we're also finding that under high loads, lubrication is quite necessary. Another area is how you manage the sealing. There are seal capabilities and wipers on the end of the linear bearing and linear guides. Those seals are very significant for both keeping the contaminants out and also the lubrication in. And one of the things that happens too in lubrication is a lot of times you see a Zerk fitting. The maintenance guy sees a Zerk fitting. The first thing he does is he squeezes grease into it until he sees grease come out of the Zerk, out of the seals. And he says, "No, okay, now I know I got it filled up with grease." But now he also knows he's got a broken seal, and now he's going to have a problem with lubrication over time. So not always having a Zerk fitting, or just because it's got a grease fitting, doesn't mean it's really a good thing to grease. Do we have any control engineers here? I don't want to offend anybody without knowing I'm doing it. You guys know what the first thing a control guy does when he gets a machine? Is he crashes it. Usually what happens is he forgets to do his limit. He always runs it into the end and it says, "Oh yeah, I forgot that limit switch." So our limit switch is hooked up, limit end stops, because what will happen is he's running the servo system without a linear guide or a ball screw attached to it, without a actuator attached to it. He's running his bunch of tests to get him going fast, and then he forgets to go back into the actual real machine parameters. The other thing that happens is you'll design on the mechanical side accelerations, loads, speeds, and a motion profile in the front end. But then the problem is on the back end, that information is not transferred over to the control guy. The control guy then starts running in his own profile, and you've overexceeded and gone past either the top velocity, the acceleration capability of the guide. But crashes is kind of self-explanatory. In normal rotary bearings, I never had to deal with crashes. Then when I get into linear, all of a sudden, that was the most common cause of a failure, is running into a stop that wasn't really supposed to be there. Failures are usually catastrophic. Sometimes you can, I've had, the guys in Detroit are great for this. It's like, how many times can I crash it before I got to replace it? And how many times can I run it over with a forklift before I got to replace it? One of the things you can do, though, is there are things we can do against crash. You notice in the contamination picture, that runner block was running into the back end of the module, and the recirculating end of the bearing was actually vulnerable. By choosing a bearing that's less crash resistant, so right here, this roll of balls is actually going to turn around and come back inside of that end cap, where a roll-on design actually This end cap is really just for seals. The rollers are all happening inside here. So if crash is going to be something we have to protect against, maybe it's something to do with the linear bearing itself. But I would just suggest using a shock absorber limit switch is probably more effective than relying on your linear guide or your runner block for crash. Any questions? Okay, thank you very much.